Hello, and welcome to an introduction to noise. My name is Steve Ellingson. Here's an outline of this lecture. First, I want to discuss about how noise determines sensitivity. This is really the fundamental issue of why we're concerned about noise in radio and RF electronics. So let's address that first. I'll talk about thermal noise. In that vein, we'll talk about the noise voltage of a resistor, and I'll show you an example. Then I'll talk about non-thermal noise. This will lead us to the concept of equivalent noise temperature of active devices, and I'll show you an example. And then we'll be ready to talk about noise factor or noise figure. These are the same concepts, just different names, and I'll show you an example to illustrate the concept. And then I'll discuss the special case of passive two ports, where we get some particular results, and I'll show you an example. So first, noise determines sensitivity. Received radio signals are typically very, very weak. The purpose of gain in a receiver is to amplify the signal to a level at which it can be detected. Now typically this means achieving a level comparable to the full scale range of an analog to digital converter, assuming your receiver uses an analog to digital converter. Not all receivers do. Many receivers, even in the year 2016, continue to use analog detection. In that case, the purpose of gain means elevating the signal to a level at which the detector, the analog detector, works properly. So whether the receiver is digital or whether the receiver is all analog, the issue is really the same. Now, gain by itself does not directly determine sensitivity. The sensitivity of a receiver depends on the signal-to-noise ratio at the input of either the digitizer or the analog detector. It depends on signal-to-noise ratio, not simply the level of the signal. Therefore, we must be concerned with the noise that appears at the detector input. So, first, let's talk about thermal noise. Atoms and electrons comprising any material experience random displacements that increase monotonically with physical temperature. So, as you probably know, at absolute zero, nothing moves. This is almost the definition of absolute zero. However, as the temperatures increased from absolute zero, atoms and electrons move. They have heat. Now these particles are typically charged. Certainly electrons are charged. So the displacement that is associated with heat, that is this tendency for things to move, is perceived as a current. And the difference in potential over some displacement is then perceived as a voltage. And we refer to this as the thermal noise. The specific physical mechanism at work here is known as Johnson noise, that's one word for it, or Johnson-Nyquist noise. Now this is an utterly random process. Heat does not cause displacement in one direction, it causes displacement randomly in all possible directions, and so this can only be described statistically. The amplitudes of these incremental voltages and currents follow a zero mean Gaussian distribution. The resulting current and voltage is then what we refer to as thermal noise. So let's talk about the noise voltage of a resistor. On the left, I have a model for a resistor. In this model, the resistor is modeled as an ideal resistance, that is a resistor which has no noise. And then the noise is represented by this voltage source, V sub n. Now, what I've done here is I've represented a physical resistor, which has thermal noise intrinsic to it, as these two things, as a Thevenin equivalent circuit consisting of the ideal resistance that has no noise, and then a voltage source which accounts for the thermal noise of the resistor. Now the circuit on the right is what I'm going to use to determine what that thermal noise is. So On the left side of the terminals here, I have simply the circuit I already showed on the left. And then on the right side, I have a load. Now the load I'm going to select is simply a resistor that has the same value of resistance as I have on the left. Now when I do this, this voltage here across the terminals is simply 1/2 V sub n. And the reason is that these two resistors form a voltage divider, so of course V sub L is 1/2 V sub n. Similarly, the current through this resistor is simply V sub n divided by 2R, because the total resistance in that path is 2R. So now I can compute the power which is dissipated in the load resistor. Now the power which is dissipated in the load resistor is a product of that voltage across the load resistor and the current through the load resistor, as usual. But these are statistical quantities, and power is a deterministic quantity, so I have to do an integration to figure out what the power is. Power is time average of these quantities, so I average over some time. That time over which I'm going to average begins at time t0 and ends tau seconds later. All right? And then the trick is to average over tau, over the time that I'm going to consider, and then I let tau go to infinity to do a proper average, because the result should not depend on tau. Now I can make the substitutions for V sub L and I sub L here, and then factor out this factor of 4R, which comes from these denominators, and that appears over here. So now I just have an integral of V sub n squared over the same duration, divided again by tau, and I take the limit as tau goes to infinity. Now this thing here, the whole thing, except for the factor of 1 over 4R out front, is the very definition of variance. Right? Variance is the statistical concept, and we represent it using the symbol sigma squared, where sigma is just the standard deviation, or the RMS quantity. In any event, this whole thing here is the statistical variance, and so I find that the power dissipated by the resistor is simply 1 over 4R times the variance of this noise source, V sub n. Now, I'm not quite done because I still don't know what V sub n is. So here's what we're going to do. We're going to note that in the resistor model, I have the ideal resistance. I have something here, which is a statistical voltage source. And I'm going to say here, this is just RMS, referring to the fact that this is not squared, noise voltage. And now I'm going to assume it's Gaussian distributed. That wasn't required previously, but now I'm going to invoke that, recognizing the fact that that is, in fact, the case for thermal noise. Once again, I'm delivering a power P sub L into this resistor, and I just worked out what P sub L should be in terms of this statistical noise voltage. Now, circuit theory from the previous page says the dissipated power is simply the variance of the noise voltage divided by 4R. However, we have this other branch of science known as thermodynamics. Thermodynamics says that the power delivered to this resistor, in this case that I've set up here, is given by the expression K times T times B. T is physical temperature. So now you see right away how we're going to make the connection to thermal noise. Thermodynamics tells us how to do that, and this quantity T is the physical temperature, the temperature at which the resistor is actually at. If it's at room temperature, then T is something like 290 Kelvin or so, for example. B is bandwidth, and K is Boltzmann's constant. Boltzmann's constant lets us convert this physical temperature into a unit of energy. So the constant is simply 1.38, and I should point out this is approximate. This is 3 significant figures here. 1.38 times 10 to the minus 23rd joules per Kelvin. Joule being a unit of energy, K or Kelvin being a unit of temperature. So Boltzmann's constant is 1.38 times 10 to the minus 23rd joules per Kelvin. And this is what thermodynamics tells us the power delivered to that load resistor over here should be. So now we see how to make the connection. I simply have to equate these two things, and now I can see how noise voltage is related to physical temperature. When I do that, set these two things equal, and then solve for sigma sub n, which remember is the RMS noise voltage, then I find that the RMS noise voltage is the square root of 4 times Boltzmann's constant times the physical temperature times the bandwidth times the value of that resistor. So now I've got it. I've got the RMS noise voltage in terms of physical quantities, the physical temperature, the bandwidth that I want to consider, and the resistance. So here's an example. Let's say I have a 1 kilo ohm resistor, a resistor which is 1,000 ohms. Let's say that resistor is at approximately room temperature. I'll call it 20 C, 20 degrees Celsius. And let's say the bandwidth is 1 megahertz. I want to consider 1 megahertz of bandwidth. Well, then T in Kelvin is simply 20, which I got from here, plus 273, which converts Celsius to Kelvin, and I get 293 Kelvin. So now I apply the equation I just derived. I make the substitution. There's Boltzmann's constant. There's the temperature. I'll leave bandwidth as a undetermined variable. And then here's the resistance. I'll multiply through. The only thing I don't know is bandwidth, so I end up with a factor of square root of bandwidth here. And then all the other numbers collapse to this constant, 4.02 nanovolts per square root of hertz. So we can see this is dimensionally correct, right? Because bandwidth is hertz, so I get square root of hertz here, square root of hertz here, and then nanovolts. And nanovolts is what we're looking for. Now, if I want to take that final step, I have to now use the fact that the bandwidth was determined to be 1 megahertz. I apply that here, and I get the final result, which is 4.02 microvolts RMS. Now, I want to make one comment about this thing, this constant that we came up with, 4.02 nanovolts per square root of hertz. This is known as noise voltage spectral density. Noise voltage spectral density, and this is used quite often, maybe less so in RF electronics and more so in analog electronics, but nevertheless this is an important thing to know about. This is the noise voltage, the thermal noise expressed in bandwidth independent units. So frequently you know this, and the bandwidth is something which is varying or which you can control, and so it's useful to know the noise voltage spectral density separate from the bandwidth. So that's why I'm identifying that factor. Okay, non-thermal noise. The definition is noise which is not thermal in origin, right? The physical origin of noise that I referred to as being thermal noise was based on heat, based on temperature. Temperature gave rise to displacement of charges. Displacement of charges gave rise to currents and voltages. But that's not the only way we can have noise. We can have noise due to other phenomena. Common types of non-thermal noise are primarily associated with semiconductor devices, and these include things like flicker noise, which is also known as 1 over F noise, shot noise, which is associated with the discrete nature of charge carriers. We know that charge comes in chunks, we call them electrons, and we don't have half an electron, for example. So we only have discrete increments of charge, and in many practical scenarios we can perceive that, and so we see not a continuum of possibilities but rather a discrete distribution of possibilities, and that gives us shot noise. And then there are certain other kinds of external noise, and we'll talk about that later. Other than the very different spectral properties, thermal noise and non-thermal noise are actually quite similar, and as we're about to show here, we can treat them the same way. We can describe them using the same metrics as long as we're careful. Right? The big difference is that over very large bandwidths, they behave somewhat differently. But over bandwidths which we practically operate over bandwidths of radio systems, for example, the thermal noise and non-thermal noise can be treated in a very similar way. And in fact, it's convenient to define an equivalent noise temperature. That is the physical temperature of a passive device, such as a resistor, that generates the same noise power. So what we frequently do to characterize non-thermal noise is we say, look, this non-thermal mechanism, this device which is producing non-thermal noise, is behaving just like a resistor at a certain physical temperature. So the idea goes like this, to show it a little bit more explicitly. In the resistor case, we had a resistor model which consisted of an ideal resistance that is noiseless, and the noise voltage separately, and it was delivering some power P sub L into a resistor having the same value, R, which was also ideal. And we also knew from thermodynamics that that has to be equal to KTB, that power delivered, where T is the physical temperature. So now in the equivalent noise temperature case, we have not necessarily a resistor, but now any one port thing producing a noise-like output. And that thing is again represented by a Thevenin equivalent circuit, which, just like the resistor circuit, has some noise voltage, who's assumed to be Gaussian and has a certain root mean square value. And we have in general an impedance. Now this impedance may not be completely real. It may be some combination of real and imaginary components. So we'll call that Z sub S, S meaning source in this case. And I'm dumping the power into a load. And in this case, the load is going to be Z sub S, the same as I had here, but now conjugate. And the reason I want to conjugate it is because I want maximum power transfer. In other words, I want this definition to apply to the case when I have maximum power transfer from the thing I'm characterizing to this test source. And in that case, then, I apply the thermodynamic concept, and I say the power delivered to that test load is K, now times an equivalent noise temperature, times B. So this TEQ is the equivalent noise temperature. It's the temperature of a resistor that would produce the same noise. So here's an example. I have a laboratory benchtop noise generator. These things exist. Maybe it's an arbitrary function generator of some kind. Maybe it's an intentional noise generator. We use noise sources for RF measurements quite often. But this gadget is characterized by its output impedance, which is 50 ohms, fairly typical. And we measure the output into an open circuit load, and we find that that's 5 millivolts RMS divided by the square root of hertz. Remember, that's voltage spectral density. So I have this device. It has a port, right? When I have nothing attached to it, I see a voltage equal to this. And then looking into this thing, I see a 50 ohm impedance. And this is then for the open circuit condition. Now, what's the equivalent noise temperature? Well, to calculate that, I just recognize that this must be the Thevenin equivalent circuit. This is the test that I developed in the previous slide. The load source, Z sub S conjugate, is simply 50 ohms. I apply the thermodynamic concept here. And I see that if I divide by B here, I get that the power delivered to the load divided by B is K times the equivalent noise temperature, all right, times V sub N squared divided by 4 times Z out. That's just the available power density, right? That's what we get when we conjugate match a load to its source. So this is the circuit theory concept for PL. And if I solve for TEQ here, I get that the equivalent noise temperature is 9,058 Kelvin. Now, again, this is the temperature of a resistor, specifically the temperature of a 50 ohm resistor, that would give us the same power density as this particular piece of lab equipment. And it tells you something about why it's a bad idea to use a resistor to do this. It would have to be at 9,000 Kelvin. 9,000 Kelvin is spectacularly high temperature, so it's much safer and more practical to generate this kind of noise using an electronic gadget of some kind. But you see how the concept applies. We can characterize this electronic gadget as if it were a resistor, and that resistor has a value of 50 ohms and would have to be at 9,000 Kelvin. So we refer to the output noise from this thing as being 9,000 Kelvin. That's its equivalent noise temperature. Now, I just want to point out here before I leave, this is not a recommended measurement procedure. I show you this example merely to illustrate the concept. The reason it's not a recommended way to determine the equivalent noise temperature of your benchtop noise generator is because many pieces of electronic equipment behave differently when they're open circuited than they do when they're properly terminated. Right? So when I did this, I assumed implicitly, without telling you, that nothing changes depending on how I load this particular piece of equipment. In other words, the device works the same when I terminate it in 50 ohms as it does when I terminate it into an open circuit. And for some pieces of equipment, that'll be true. For other pieces of equipment, it will not be true. So you have to be very careful. This is not a recommended measurement procedure unless you really know that this is a safe thing to do.